Hi, everybody. Very good morning. So there was some confusion, right? There was some confusion between the management. So that's why we couldn't have the class at the prescribed time period, right? So we'll start it now, right? Okay. So let me share my screen. Excuse me. Yeah. So hope you remember what we saw last class, right? So we saw, I think, right, we saw about naming, IUPAC naming we saw, right? Very important, right? I told you that a direct 5 mark might come from this, right? From the coordination compounds. Okay, then we went on, isomerism is not there as you told me, right? And we went on to see this bonding, how the bonding happens in case of coordination complexes, right? So the first one we took was valence bond theory, right? So in valence bond theory is nothing but theory of hybridization, right? And we told that we are going to look into only two of the complexes, two of the coordination numbers. One is coordination number 4 and coordination number 6, right? So for coordination number 4, we can have two different things. One is square planar complexes. The other one is tetrahedral complexes, right? So square planar complexes, you know how the shape looks, right? This is how the shape will look here, what I have written here, right? And you know how tetrahedral looks, right? And we know this wedge and dash, what they represent, right? The wedge is the wedge means the bond is coming towards you, and dash means the bond is going away from you. Okay, right. And then we said for square planar complexes, the hybridizations would be DSP2, right? Why we write D first is because this D is going to come from the penultimate shell, the n-1 shell, not the valence shell, but the next before that, right? The before one, the shell which is before your valence shell, n-1 the shell. That is why these are going to be called as inner orbital complexes, right? And in case of tetrahedral, the hybridization you can expect is sp3, right? And here there is no d orbital here, but again this s and p are actually going to be from the valence shells, right? And that is why these are going to be called as outer orbital complexes, right? And then we saw about the coordination number 6, which had octahedral complexes, right? Even though we are going to have two different hybridizations, but both of them will have same shape only, the same geometry only, that is octahedral. But again, coordination number 6 or octahedral complexes can have two different types of hybridization, sp3d2 or d2sp3. Again, this d2sp3, this d comes from your inner shell, right? So that is why it is going to be called as inner orbital complex. And in case of sp3d2, this d is going to come from the valence shell, and that is the reason why it is going to be called as outer orbital complexes, right? Okay. Now, for us to understand how exactly the bonding happens in case of coordination compounds, right? And we know that inside the coordination sphere, all the bonds are actually going to be coordinate bonds, right? So for us to understand how coordinate bond works in terms of hybridization, we took this example BF4 minus, right? We said that the steric number is 4. There is a formula, and we know it is sp3 hybridized, right? So we saw how this works, right? So we understood that there is 2s2, 2p1 is the valence electron configuration for boron, right? So this electron 1 got shifted. So we have in this one and in this 2 electrons, right? And totally we have sp3. Now what we understood is that we have 3 totally. Again, the most important thing is the number of atomic orbitals combining should be equal to the number of hybrid orbitals formed, right? So here we have 4 atomic orbitals combining. So we should be forming 4 number of hybrid orbitals, right? So we have all the 4 hybrid orbitals having 1 electron coming from boron. 3 of them will be there. And one of them you saw was empty. Okay, one of them you saw was empty. So obviously we have, that is okay, right? So the first 3, that is each having one electron coming from boron, are going to form normal covalent bonds. Like 1 electron come from fluorine, 1 electron come from boron, normal covalent bonds here, right? But this one, which was empty, which is going to come from F minus, both the electrons are actually going to come from F minus only. That is a coordinate bond, right? And we even saw how this works in case of a Lewis-Dot structure. We understood that these 2 electrons are actually going to be donated to your boron coordinate bond. Okay. So what we can conclude is that the number of, where is it? Yeah, the number of coordinate bonds which in a molecule is equal to number of hybrid orbitals. Number of, not number of hybrid orbitals, number of empty hybrid orbitals. Right? So for example, a coordination complex is having a coordination number 4, right? That means it should have 4 coordinate bonds. So it should have 4 empty hybrid orbitals. If at all I have 6, means coordination number 6 means I need to have 6 empty hybrid orbitals. Okay, very, very important, right? And that is, so now we can expect how the this thing is going to look. Is it not how the hybridization is going to look? We are going to have all the hybrid orbital which is going to get formed is going to be an empty hybrid orbital, so that they will be able to go for hybrid. They'll be able to go for coordinate bonds, right? This is what we saw last class, right? Any questions anybody has in this?
No, sir.
Okay, right. So with that being said, right, now we'll take some specific examples. But before we move on to the example, we have to know something called as spectrochemical series. Right. So what is the spectrochemical series? If you ask me, spectrochemical series is nothing but arrangement, or say arrangement of all the ligands, right? All the ligands in the ascending order, of their strengths. Okay. The spectrochemical series is what? It is the arrangement of ligands in their ascending order with respect to what? With respect to their strength of ligands. Okay. Right. So generally, we have something called as weak field ligands, or we call them as weak ligands. Right. And we have some intermediate, like intermediately strong ligands. Right. And obviously we have something called as strong field ligands. Okay, weak field ligands, intermediate field ligands, and strong field ligands. We have obviously weak field ligands means the strength of the ligand is very weak. Strong field ligands means the strength of the ligand is very strong. Okay, right. Now, this you don't have to worry how we are going to do this, right? How is it that the spectrochemical series come? Why is it that say Cn minus ion is a stronger ligand than say Cl minus ion? Right? Or say carbonyl is going to be a stronger ligand than say NH3, something like that, right? You don't have to worry about how they are arranged. That is beyond the scope of 12 class, right? But we have to know what is spectrochemical series. What is the arrangement which we have to know, right? Let me see if I can see a picture of this in Google. I want a good one. If it is given, whatever is given in NCERT, that at least if I get that is also going to be good. Okay, no issues. We'll take something. This only is best, right? I will take this. Hello, 1 second, people. 1 second. Just give me 1 minute. I have to pick up. This call is very important. Okay, I'm so sorry. 1 second. Okay, right. So I said that we have to know the spectrochemical series. Spectrochemical series is nothing but the arrangement of ligands with respect to their strengths, right? So this is the spectrochemical series, right? And we have to remember this. Okay. Now I would say till H2O. Right, let me use some. Right, till H2A. Right. So till H2O, I would say, okay, or I would say till O2 minus, right? They are weak field. Right, and this part, this till NH3, I would say till bipyridine, even till NO2 minus, I would say these are intermediate. Right, and all the other ones you see, C and CO and all are strong field ligands. Okay, right. So, but again, what you have to understand is if at all the intermediate ligands are coming, right, mostly they will give you NH3 and H2O. If H2O comes, you have to consider as weak ligand, and if NH3 comes, you have to consider as strong ligand. Okay. Other than that, whatever you get, say I minus, Cl minus, Br minus, whatever you get, those are weak field. The moment you see Cn minus or CO, that is definitely going to be strong ligand. Okay. See, we will be using only generally this X minus in your for most of the cases. X minus, that is your I minus, Br minus, Cl minus, F minus will be using, right? That is definitely going to be weak. Right, and we'll be using this H2O also, that again is going to be weak, right? And we'll be using ammonia, which will be strong, right? And we'll be using the CO and Cn minus, which is again going to be strong. Okay, now these are all the common things which you'll be using in your valence bond theory as well as in any other theory which you're going to see. Okay, this at least you have to remember. Okay, X minus, H2O, NH3, CO, and Cn minus, whether they are weak or strong, we have to know. Okay, now why am I specifying so much about these weak field ligands and strong field ligands? Okay, now what we have to understand is, people, whenever a strong field ligand is there, right, whenever a strong field ligand is there, they will go for forced pairing. Right, they will go for forced pairing of electrons in the metal. Right, so whenever you have unpaired electrons in the valence shell, right, and if you have a strong field ligand like say CO or Cn minus or NH3, right, they will go for forced pairing of these electrons in the metals valence shell. Okay, and after pairing only, you have to go for the hybridization. Right, when you go for examples, it will be very more clear. Okay, but if at all we have weak field ligands, no such thing will happen. You can directly go for the hybridization, whatever you get. Right, so make sure you remember this. And you can ask me, sir, why is this happening? Why is it that when I have a strong field ligand, we have a forced pairing happening? That question will be answered in CFT. Okay, in crystal field theory, we will try to understand why exactly is there a pairing happening here. Why is there a forced pairing happening here? Right, for now, just know it. I will answer this question, why this forced pairing happens in your CFT. Okay, fine. Now let us take some examples. Right, maybe a moment. I will take some good examples for you. This is physical chemistry. Just a moment, people. Just give me 1 second. Oh, we actually forgot Werner's theory. Okay, we'll see that next. That was the first theory, okay? Anyways, we'll see that later. Okay, the first compound which we'll take is, right, NiCO 4 times. Okay, this is the coordination complex, and we are going to see how the this thing is going to happen, how the hybridization is going to happen, how the bonding is going to happen. We'll try to understand. Okay, right. So people, right. So obviously, as I said, we will be doing hybridization only for the central metal atom. Please remember this, right? We will be doing hybridization only for the central metal atom and not for the ligands, right? Okay. So all you have to understand is first, what is the oxidation state of the metal first? Okay. Now in this case, you understand this is a neutral ligand. I know, sorry, this is a neutral complex. I know the ligand is also neutral. Right, so I can actually tell that the nickel is going to be in its 0 oxidation state. Okay, the nickel is going to be in its zero oxidation state, and we know CO ligand is a strong ligand. Okay, we know that CO ligand is a strong ligand, right? So let us try to understand now. Right now, the moment you see what is the coordination number, the coordination number here is 4. So either you can have octahedral, either you can have tetrahedral or you can have square planar, depending on what kind of hybridization you will have. Remember this, DSP2 is square planar, right? And if you have SP3, that is tetrahedral, right? You have to remember this also. Okay, so now let us write the configuration, right? Now people, like one very important thing is we have to remember the electronic configurations of the 3D series at least, right? So we have in the D and F block elements, we have the D block elements where you have 3D series, right? We have 3D series, 4D series, and the 5D series, right? So hope you remember the metals also. Like you don't have to worry about the 4D and 5D. Don't worry about it for now. But at least 3D, we have to know the elements and the electronic configuration, atomic numbers, everything should be there in our fingertips because they will not give you in exams. Okay, right. So let us do that. So first element is scandium. Then you have scandium, titanium, vanadium, right? Then you have scandium, titanium, vanadium, chromium, manganese, cobalt, nickel, or is it nickel, cobalt, or cobalt, nickel? Manganese?
Cobalt, nickel.
Cobalt, nickel only. Okay, cobalt, nickel. Then you have, I think, iron, right? Cobalt, nickel, iron. Then copper, zinc. Is it correct? 10 elements are there. 1, 2, 3, 4, 5, 6, 7, 8.
Cobalt, nickel, copper, and zinc. So.
Oh, where did I miss iron then? Iron should come right somewhere.
After
I think
manganese.
after manganese, it's iron.
Yeah, yes.
Yeah, exactly right. Good. Right, so manganese, iron, cobalt, nickel, copper, zinc. Yeah, so these are all the elements we have. Right. So the moment you know at least the order, it is very simple for us to know what is the configuration. It is very simple. The atomic number is going to change from 21 to 30. 21, 22, 23, 24, 25, 26, 27, 29, 30. Okay, that is all right. So remember that all of them will have one thing in common. 4s2 will be common for all of them. Okay, 4s2 will be, not for all of them, but chromium and copper will have a little difference, but still, for most of them, 4s2 will be common. Okay, right. So the moment you remember 4s2 will be common except for chromium and copper, right? All the others, what you have to do is if it is 21, right, we will write 4s2 3d1. That's the valence electron configuration. Same way for titanium, it is 22. We'll write 4s2 3d2. Same way for vanadium, it is 23. So it is going to be 4s2 3d3. For chromium, what we expect? We expect 4s2 3d4, but I know half fill stability is more stable. So we will write this as 4s1 3d5. Right? So it should be for 24, obviously. So we expect 4s2 3d4, but we know half fill stability is going to give a lot of things, right? So we have 4s1 3d5, right? And for manganese, it is 25. So we will have 4s2 3d5. For iron, it is 26. So we write 4s2 3d6. For cobalt, it is 27. So we write 4s2 3d7. For nickel, 28. So it is going to be 4s2 3d8. And for copper is going to be little this thing. So we expect it is 29. So we expect that it is going to be 4s2 3d9. But again, we can have a fully filled configuration. That would be better, right? So we can write 4s1 3d10. That's the way to write it. Okay, that's why I said for chromium and copper on, we are going to have 4s1 because of half filled and fully filled stability. But for all the others, we are going to have 4s2 common. Right? And obviously for zinc, we are going to have 4s2 3d10. Right? So this is what we have to remember. The electronic configuration, the valence electronic configuration and their atomic numbers are going to be very important. Okay, if you don't remember this, I'm so sorry, you will not be able to answer simple questions also. All right. Okay, fine. So now we took the example of nickel CO 4 times, right? That is, I should write this properly. This is capital O. Okay, fine. So nickel carbonyl, the name of the compound, if you ask me, it is going to be tetra carbonyl nickel. 0, obviously, and the oxidation state is 0. Right, that's the IUPAC name of this compound, tetra carbonyl nickel. Anyways, so let us try to understand how the bonding is going to happen, how the hybridization is going to happen. Right, so we have nickel. And we understood that the electron, it is 28. So we have 4s2 3d8. That is what we have. 4s2 3d8. Right. And yeah, this is enough for us. Right. 0, what is that? The electronic configuration is 0. No issues. Okay. Now it is, see, this 3d is going to be inertial, right? So it is better to write. It is better to write it like this. So we can write it as 3d8. 4s2, 4p0, 4d0. Like this we can write, right? Because in the fourth shell, we have only s to be filled, p and d are not filled at all. No issues. Okay. Now let us go for this thing. Let us go for the diagram, right? So we have d means we are going to have 5, right? So we have 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. No issues. And in 4s, we have 2 electrons. In 4p, we have 0 electrons, right? In 4d also we have no electron. This is 4s, this is 3d. Okay, right. Now people, very important thing is that the pairing needs to happen here. Why pairing needs to happen? Because we have already understood that your CO is a strong field ligand. So we have to make sure that you have unpaired electrons here, Those unpaired electrons should get paired, right? Those unpaired electrons should get paired to form a paired electron. Okay. Now this is in absence of the ligand. Right? In the presence of the ligand, what is going to happen? This is how it is going to look. Okay. So we are going to have like this. Okay. Now, obviously one space is becoming empty, isn't it? One space is becoming empty. So you can shift this paired electron to the empty space. Okay. The 4s electron which was paired, you can shift it to the previous place. Okay. Done. Right. So we can write this as 3D. Done. So what do we have? We have 4s to be empty. We have 4p to be empty. And obviously we have 4d also to be empty. Okay. Right. Now, what I said, I said that here you can either have the coordination number is 4, either you can have tetrahedral, that is you can have sp3 hybridization, or you can have square planar complexes, which is going to have dsp2. Now, the most important thing about hybridization in case of your coordination compounds is that all the hybrid orbitals should be empty. We have already established this point very clearly. Right? Since all the bonds in the coordination complex is going to be a coordinate bond, all the hybrid orbitals which you are forming should be empty. Right? Now, you cannot take this d orbital. There is no possibility that these d orbitals can involve because all are filled. Right? It is impossible for us. Right? So the only way which we'll be able to make sure that we can have a coordination number 4 complex is by taking this particular S, P1, P2, P3. Okay, by taking this S, P1, P2, P3. Right? So we can have 4 numbers of sp3 hybridized orbitals. Right? 4 numbers of sp3 hybridized orbitals. And obviously to all of them, CO is going to come. CO is going to come, donating its lone pair, forming a coordinate bond. Okay, right? Be very careful with this. The only thing which you have to remember is 2 things you have to remember. One is when strong field ligand is there, forced pairing will happen. Whenever you have unpaired electrons, go for pairing them. Second thing is that whenever you have, second thing is that the hybrid orbitals, right? They should be empty in case of coordination complexes. Right? So now that those 2 things you remember, now we understand it is going to be sp3 hybridization. So now you can make a makeup of so many things. First point is that it is going to be a tetrahedral complex, right? Because it is having sp3 hybridization. Second thing is that it is going to be an outer orbital complex. Now you understand that the valence shell is fourth shell, right? The valence shell is fourth shell, and both the S and P's are coming from the outer shell. That is the valence shell. So definitely here it is going to be an outer orbital complex. Right. Now, one more thing is, since you have no unpaired electrons here, right? Since you have no unpaired electrons here, their spin will be very less. So whenever you can also remember this, the outer orbital complex will always be called as low spin complexes. Right? This outer orbital complexes will always be called as low spin complexes. Okay. Now, why they're going to be called as low spin complexes is because their magnetic moment. Is it called magnetic moment? Yeah, magnetic moment is very less. Actually, it's zero. Okay, the magnetic moment is zero. Now, hope you remember, people, how do you calculate the magnetic moment? Magnetic moment is denoted by the letter mu, right? And that is equal to root of n into n plus 2 bm. What is bm? Bm is the unit. Bm is the unit called as Bohr magneton. Okay, right. So this n is what? N is the number of unpaired electrons. Right? N is the number of unpaired electrons. Right? Now, in this case, what you see, there are literally no unpaired electrons. All the things are paired. So obviously the N is zero. So the magnetic moment is zero. Okay. So that's the reason why we are going to call them as low spin complexes. And you can in general decide that all the outer orbital complex will be a low spin complex. Okay. So all these three things can be decided the moment you decide the hybridization. What is the hybridization? Okay, right. So let us take one more example. Right, let us take one more example. Is there any questions anybody want to ask? How this is happening, how that is happening, and any of that question? Okay, fine. I suppose
could you show the formula of the compounds?
Yeah, what formula? Oh, the magnetic moment formula. Yeah.
Even the compound we did for nickel. So.
Compound?
The nickel compound which we did.
Yeah, it is NiCO 4 times. Okay, we'll look at the orbital configuration also, how is it going to look, and how we are going to make the hybridization. Everything should be clear. See, like this you should write, okay? If they ask you to discuss the bonding in case of this compound with respect to valence bond theory, everything, whatever written except for the configurations here, don't worry, don't write the full configuration and all. Just write nickel, right? What is the electronic configuration? Show the orbitals, right? And if at all I have strong field, again, show the pairing happening, right? And then you show the empty hybrid orbitals like this and show the coordinate point. And then you have to write all these 3 points, whether it's tetrahedral or octahedral, outer or inner orbital complex, high or low spin complex. All those things you should write. Okay. Can we move on?
Yes.
Okay. Right. And one more thing also. So you can talk about the magnetic behavior. Okay, we can talk about the magnetic behavior. We know for paramagnetic substances, right? For paramagnetic substances, at least one unpaired electron should be there. Right? At least one unpaired electron should be there, right? For anything to be paramagnetic. Now, in this case, what are you seeing? You are seeing that none of them is paired. Everything, no, none of them is unpaired. Everything is paired. Okay. So you can conclude one more point also, that this particular complex is going to be a diamagnetic complex. Okay. This particular complex can be a diamagnetic complex because for paramagnetic species, we will have at least one unpaired electron to be present. Okay, now since you can even write it here, for diamagnetic substances, no unpaired electrons. Okay, for diamagnetic substances, there shouldn't be any unpaired electron present. Very simple. Okay, so all these things you will be able to decide the moment you form the hybridization. Everything can be decided. Okay, we'll take one more example. Okay, so the same compound, same thing we will take, but in this case, I'm going to take a weak field again. Okay, right? Right. Okay. So people, in this case, the first thing you will do is find the ligand is Cl minus. So it's a weak field ligand that we understood. Right. And coordination number is 4. Right. And we have to find what is the oxidation state of nickel first. The oxidation state is X is the oxidation state of nickel. -4 equal to -2. So X is going to be in +2 oxidation state. So nickel is going to be in +2 oxidation state. These are all the first things you will do. First, see what is the ligand. Decide whether it is going to be a weak field ligand or a strong field ligand. That's the first thing. Second thing, look at the coordination number, whether it's coordination number 4 or coordination number 6. Third thing is that you have to find the oxidation state of the central metal. Once you are done with all this, then we can go for your orbital configuration. Okay, so nickel, right? Nickel, I know the valence electronic configuration is what? 3d84s2, right? So when I say Ni2+, now remember people, whenever we want to remove electron, we will always remove electron only from the valence shell, right? We will remove electron only from the valence shell. So the valence shell here is 4. So we have to remove these 2 electrons only. So Ni2+ will have 3d8, 4s0, 4p0, 4d0. That would have been the configuration. Be very careful with this. These, like when I was student, I was always confused. Okay, I have to remove 2 electrons, but where? Whether from 3d or from 4s. We always remove electron only from the valence shell. Remember that. Okay, right. So that being said, now you can go for the orbital configuration. Say 3d. We'll draw. Okay, so we have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Right. Okay. Now that is your 3d. Now we can go for 4s, which is empty, and we have 4p also, which is empty, and then we have your 4d also, which is empty. Okay, right. Now people, here you have what? Here you have Cl minus, which is going to be a weak field ligand, so no pairing. Right, here we will not go for any forced pairing. That means here we have 2 electrons, right? They are not going to go for any pairing. They will be staying as such only. Okay, right. So the only possibility we can do is that again you can go for the coordination number 4. So either you can go for D2sp2 in DsP2, or you can go for sp3. Again, since there are no empty orbitals available, the only possibility is to go for this sp3 hybridization again. Right, sp3 hybridization again. Right. Okay. So now what can happen? Right. Let us look into this. So we will have 4 numbers of sp3, 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 and sp3 hybrid orbitals, right? And everything is empty. So all of them is going to come from CO, not CO in this time, is going to be Cl minus, Cl minus, Cl minus, Cl minus, Cl minus, right? And all of them are going to have 2 electrons coming only from Cl minus. Okay. Right. So now what all we can decide? The moment we decide that the hybridization is sp3, we can conclude the fact it is indeed going to be tetrahedral, right? And it is going to be what to say? It is going to be a outer orbital complex. Outer orbital complex.
It's paramagnetic, sir.
Sorry.
It's paramagnetic, right, sir?
Yeah, it is paramagnetic. Yes, absolutely. Right. And the moment you see unpaired electron present. Right, the moment you see unpaired electron present, you can write them as high spin complexes. Right. So I told you in the previous case that generally outer orbital complexes will be low spin complexes. You don't have to take that. That's wrong. Okay. The moment you see unpaired electrons present, right, they will always be high spin complexes. That is how we decide. Okay. If this is going to be a high spin complex, right, and obviously it is going to be paramagnetic in nature. It is going to be paramagnetic in nature. Okay, right? So the only difference is last time pairing happened, this time pairing didn't happen. That's the only difference here. Everything else is same except for high spin and low spin also. And paramagnetic and diamagnetic. Right? So these are all the differences we see. Okay, right. Let us go for another question. Right, another example we'll take. Right. So in this case, let us take NiCN 4 times 2 minus. Okay, NiCN 4 times 2 minus. Now again, if you check, now in this case, Cn is going to be a strong field ligand. Right? So pairing will happen. Right? And Ni again, if you calculate, it is going to be in +2 oxidation state. No issues. So again, Ni Ni will have 3d8, 4s2. So obviously Ni2 plus is going to have 3d8, 4s0, 4p0, and 4d0. No issues, right? Okay. So let us write the orbitals. 1, 2, 3, 4, 5. So we have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. That is 3d. Okay. Now we have 4s to be empty, 4p also to be empty, and we have 4d also to be empty. Right. Now this is in absence of the ligand. Right. Now, in the presence of the ligand, since we have Cn minus 1, what is going to happen? We are going to have forced pairing happening. Is it not? Right? We are going to have forced pairing in the presence of the ligand. Right? What is going to happen? These two are going to get paired. Right? So, we will have 1, 2, 3, 4, 5, 6, 7, 8. Done. Right? Now, we have S to be empty and we have your P to be empty. Don't worry about D. It is not going to be useful here. Okay, this is 3D, right? This is 4s and this is 4p, right? Now I told you that you should have all the hybrid orbitals to be empty in order to form your coordinate bonds, right? Now you can see, since I have empty from here itself, that is from the inner shell, you can take it from here itself. Last time we did not have the luxury of taking here because this was not empty at all, right? But this time, one of the inner orbitals are becoming empty. So the overall hybridization, if you look, we took one d orbital, one s orbital, and two p orbitals. So we are going to form 4 numbers of hybrid orbitals, and all of them are actually going to be dsp2 hybridized orbital. Now this D is coming from 3 and the S and P are coming from 4. That is, the valence shell is coming, S and P are coming from the valence shell, but the D is coming from the inner shell. Right? So obviously all of them will be empty now. Right? Now you have your Cn minus, let me use this color. Right? Now we have your Cn minus, Cn minus, Cn minus, Cn minus. Right? Now that is going to donate 2, 2, 2, 2 electrons each to form a coordinate bond. Right? The moment you decide the hybridization, a lot of other things can be decided now. This is going to be a square planar complex. Right? This is going to be a square planar complex, and it is going to be an inner orbital complex because we are using your inner d orbital. Right? It is going to be an inner orbital complex. Right? And then what we can say? We can say that it is going to be a low spin complex because it doesn't have any unpaired electrons again. No unpaired electrons are there. Low spin complex. Right? And also we can say that it is going to be a diamagnetic substance. Right? Why? Because again, it doesn't have any unpaired electrons. No issues. Right? So like this only you should be doing. Okay. Right. Fine. Just looking for a better example. So that you can do it. Okay. So can you do this now? Right. Say if I take MnCl4 2 minus. Go for it. Show me the bonding. And tell me all the other things. Outer orbital complex, inner orbital complex, high spin, low spin, diamagnetic, paramagnetic, tetrahedral, square planar, all those things you have to tell me now. Go for the bonding first. This is MnCl4 2 minus. So once Jordan, maybe you can send me in WhatsApp. I can check. Now, today, when is the match for India West Indies? Do you know?
Evening, sir. 7 o'clock.
7 o'clock. Oh? Okay. I think someone sent me. Okay. No pairing. Okay. But you have to show what to say. You have to mention what orbitals you're taking, 3D, 4S, 4P. All those you have to mention. And the other things are okay, I guess. Yeah, 3D7, 4S0. 3D7. 3D5, 4S2. So Mn2 plus will have 3D5 only, right? You have taken more number of electrons. Okay. Anybody else wants to send me?
So it'll have 7 rays in the orbital.
Yeah, it is going to be 27. So what is the configuration? 3D5, 4S2. Correct?
Yes, oxidation state is +2.
Okay, oxidation state is +2. So what will you do? You'll remove 2
So
electrons.
2 will go to the d orbital. So
Hey,
it'll be
2 will be
3d7.
removed. 2 will not go to d orbital. 2 electrons will be removed. What we did here? Ni2 plus. We said 3d8 4s2. When I say Ni2 plus, what happened to this? This went out. Done. It became 4s0. 3d8 is 3d8 only. Are you able to understand? Right?
Understood.
Yeah. Okay. Yes. Anybody else want to send me? Maybe I'll give you one more.
It'll still be sp3, right, sir?
Yeah, sp3 is correct. The sp3, all the other things are correct, but it is not 3d7. It is 3d5. That's it. Okay, fine. I think I will do it. Right. So Mn is okay. First, Cl minus, weak field ligand. Right. So no pairing. Right. Weak field ligand, no pairing. Right. So Mn is going to have, okay, fine. And if you check the electronic configuration, I mean, if you check the oxidation state, right? Oxidation state is going to be +2. You can easily say x minus 4 equal to -2. So obviously x is going to be +2, right? And we understand that the coordination number is 4. That is also okay, right? Okay, now we'll go for it. Mn is going to have 3d5, 4s2, right? And if I go for Mn2 plus, these 2 electrons are removed. All that we have is 3d5, 4s0, 4p0, 4d0 is also there. Don't have to worry about it, right? Okay, now let us draw the orbitals. Okay, 1, 2, 3, 4, 5. 5 electrons in 3D. Okay, and we are going to have 0 electrons in 4s, and we are going to have 0 electrons in 4p. No issues. Okay, right. Now again, the ligand is going to be Cl minus, so there is no pairing here, right? So obviously we cannot take any orbital from 3D. The only way we can make coordination number 4 is by making 4 hybrid orbitals coming from s, p1, p2, p3. So we are going to have 4 numbers of this. Each of these are going to be sp3 hybridized, right? And obviously the Cl minus 1 is going to come, right? And it is going to donate 2, 2, 2 electrons in all of them, right? So the moment we decide sp3, right? So it is going to be tetrahedral, right? And it is going to be high spin complex. Before that, we can even write outer orbital complex. Okay, anyways, high spin complex because we do have unpaired electrons, right? High spin complex, right? It is outer orbital complex, right? And you can say that it is going to be diamagnetic, right? All these things can be set. Very, very easy. Okay, right. So with this, you can even now like, even though I am not like even if I am not teaching you about coordination number 6, right? You know that instead of 4 orbitals, instead of 4 hybrid orbitals, we need to make 6 hybrid orbitals. That's the only thing. Again, pairing, no pairing, all those will depend on what kind of ligand I have, right? So let me check whether I'm able to do this, right? Fine. So if I take right, if I take Fe H2O 6 times 2 plus, this is what I have, 3 plus or 2 plus. 1 second, yeah, it's 3 plus. Okay, now you see that the coordination number is 6 people. Be very careful, and I told you H2O, if it is there, you will consider it as, even though it is an intermediately strong ligand, we will consider it as a weak field ligand. Okay, but if ammonia comes, then we will consider it as a strong field ligand. Okay, you try this out, and anyways, I'm going to help you. Go for it. The shape is octahedral. No matter whether I'm going to have D2sp3 or whether we are going to have sp3d2, we are not going to have any change in shape. It is still going to be what? It is still going to be octahedral only. Okay, go for it. Yes. Done?
Done, sir.
Okay. Right. So let us try this. Right. Okay. So we have Fe to have 3d6. So it is going to be 26 atomic number. Anyways, okay. So here we have H2O, and I told you
3d6
that,
forest tools.
sorry.
3d6 forest tools.
Yeah, 3d6 forest is correct. Okay. So someone has sent me. Let me check. I think it's Rohan. Yeah. Okay. Okay. It is not going to have SP to D to octahedral paramagnetic and high speed. Yeah, I think it should be correct. Okay. Right. Good, Rohan. Right. So we have, it's a weak field ligand. So it means no pairing will happen. Right. No pairing will happen. So now the coordination number is 6. That is also done because we have 6 monodentate ligands. Okay. And if I calculate the oxidation state, X plus 0, because H2 is a neutral ligand, so it does not have any this thing. So X is going to be plus 3. Okay. X is going to be plus 3. Okay. That's the oxidation state of iron is going to be plus 3. That is decided. Okay. So we have iron to have 3d6 4s2. Right. 3d6 4s2. Right. Now, if Fe is going to be in Fe3 plus state, so we need to remove 2 electrons from here and obviously 1 electron from here. So all that we'll have is 3d5, 4s0, 4p0, and 4p0. This time the d orbital is going to be important. Okay. Right. Next, let us draw the orbitals. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 electrons here. This is 3d. And we have 4s having 0 electrons, 4p having 0 electrons, and also we have 4d having 0 electrons. Right? So you understand that in this case we have H2O, which is a weak field ligand, so no pairing will happen. So there is no other way than to make 6 hybrid orbitals coming from S, P1, P2, P3, D1, D2. Like this. Okay, D1, D2 like this. Okay, that is how you can show the hybridization here, right? So now I can show you the hybrid orbitals 1, 2, 3, 4, 5, 6, and all of them are going to be sp3d2s. Right? Now what we have? We have H2O coming as a ligand. Right? We have H2O coming as a ligand, H2O, 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 and H2O coming as a ligand. And they are going to donate 2, 2, 2 electrons. Okay. Done. Right? So the moment we know it is sp3d2, sp3d2, sorry, sp3d2. So it is going to be, you have to remember the shape. The shape here is going to be octahedral, irrespective of whatever the hybridization is. The moment you see coordination number 6, it is going to be octahedral. Okay. So since we have sp3d2, it is going to be an outer orbital complex. Right? And since we have unpaired electrons, it is going to be a high spin complex. Right? And obviously, since we have unpaired electrons, it is going to be a paramagnetic complex. All these things can be decided. Okay. Right. Good. Now what we'll do is another example we'll take. Right. So this time we are taking chromium Cr NH3 6 times 3 plus. Okay. Go for it. Sure.
Sir, I have a doubt, sir.
Yeah, tell me, Kanna.
In the 4d orbital, why are those 3 orbitals left out?
Here, these three orbitals, that's it. They're not going to involve in bonding. That's it.
Oh, okay.
It's as simple as that. Right? You don't have to worry about them. The 2 of the d orbitals are involved in bonding. The other 3 orbitals are not going to have any electron. That's it. They are neither involved in bonding, nor they're going to have any electron. They're just left out. Done. Yes, guys. Is it okay? Done?
1 minute, sir.
Okay. Guys, I'll mute myself. There is some background noise. Yeah, it's correct. Okay, Rohan, what you sent. And please bear with the background noise. Like someone. This Mylapore, it's a good place to stay, heart of the city and all, but this religious, torture is always there. Anyways.
I
Okay.
have a doubt, sir.
Yes,
In
Kana?
what I sent, actually. I have a doubt in what I sent.
Yeah, tell 1 second. Let me finish and then I can ask you a doubt.
Okay, sir.
Okay, right. So chromium. Okay, first we have coordination number 6. So definitely octahedral. That's okay, right? And I told you that ammonia has to be treated as a strong field ligand. Right, that is also okay, right? And let us calculate the oxidation state. You can easily calculate the oxidation state to be +3 because this is 0 and overall charge is +3. So the chromium is going to be in a +3 oxidation state, right? So we know chromium is going to have 4s1 3d5, or well, let me write this properly. We'll write it as 3d5 4s1, right? That is how we write it because we have half field stability. Right, and we can write Cr3+ means 1 electron removed from here, and obviously 2 more electrons should be removed from 3d5. Right, so all that we'll have is 3d3, 4s0, 4p0, and 4d0. Right, let us write the orbitals. 1, 2, 3, 4. So we have 3 electrons here, right? And then strange. Okay, I understand what doubt you have. So here we have this thing. What is that? 4s0, 4p0, right? And we have 4d also to be 0. Right. So now if we have ammonia, let me check what is happening here. Where are you? CuNH3. Okay, now the question is, right, even though you don't need to go for pairing, right? Even though you don't need to go for pairing, right? You understand that I can easily make D2sp3 here very easily, right? Even though you don't go for pairing, right? But if you go for pairing, it might get a little complicated. This is your 3D, right? Okay, if you go for pairing, right, all that we would have had is like this. Okay, now you can tell, sir, I can have D3sp, something like that, right? But these kind of hybridization doesn't exist, right? These kind of hybridization doesn't exist, right? So why we generally go for pairing is that we can take the inner d orbitals. Okay, we can take the inner d orbitals, but if at all we have already unfilled inner d orbitals, we do not have to go for pairing. Okay, we do not have to go for pairing. Okay, so if you go for pairing also, that, see, the thing is, if you have 3 electrons, right, 3 electrons going for pairing is not a good choice. Like at least 4 electrons, right? At least 4 electrons you should have for me to go for pairing. Okay, I think that was your doubt, isn't it, Rohan? Or is it something else? Is anything wrong? Current went off. Guys, is it okay? Are you guys there?
Yes, sir. It's fine, sir.
Okay. Right. So all that you have to understand is we don't have to go for pairing if you have already unfilled d orbitals inside itself. Okay. Don't worry about this. Right. So again, the hybridization is going to be D2sp3. Right. D2sp3. So you don't have D3sp2. So nothing like this exists. Okay. Right. So with that being said, again, the moment we write D2sp3, we're going to write it as an inner orb. Okay, first it is octahedral, right? And it is going to be what is that, inner orbital complex, because we're taking the inner d orbital. 3d is getting involved, right? Inner orbital complex, right? And we have 3 unpaired electrons also. So it is going to be high spin complex, right? And since we have unpaired electron, this is going to be a paramagnetic complex. All those things can be said. Very, very easy. Okay. So like this, any compound given to you, you will be able to go for this. What is that? Hybridization, and tell what is the shape, what is the type of complex, paramagnetic, diamagnetic, all those things can be predicted. Okay. Right. You solve more questions, whichever are there in your textbook, at least whichever is explained, that at least you understand, that is going to be more than sufficient. Okay, and what you have discussed here also, right? Okay, now that is about your valence bond theory, right? Now, what are the disadvantages? What are the demerits of your valence bond theory? The first thing is, right, why strong or weak, right? Why certain weak field ligands are there and why strong field ligands are there? What is the basis of deciding whether it's strong or weak is not known. right? That is not explained. Second thing is why pairing happens, right? Why pairing happens when we have a strong field ligand, right? That is also not explained. Okay, why we have pairing happening in the presence of a strong field ligand and why is it not happening in the presence of a weak field ligand is again not explained, but that is explained in your next one. Okay, that is explained in crystal field theory. Okay, next one is, right, the color of compounds, right? You will see that the coordination compounds are going to be very colorful species. Okay, almost all of them are going to be colored. Okay, but why do they have color is again not explained. Okay, and another thing is the strength of complexes, right? I would say the strength of coordinate bonds, right? We understand that coordinate bond is getting formed, okay, right? But the strength of coordinate bonds is again not explained, right? So these are the main problems we face in case of valence bond theory, right? So many things are not explained. Even, we understand that the bonding is explained, how a coordinate bond, why this coordination number, why this shape, why this geometry, all those things are explained, but so many things like this are not explained also. Okay, right. So actually we should go to crystal field theory, but before this we forgot one important theory. Before valence bond theory, I should have explained to you Werner's theory, right? Okay, that we'll see now, right? So we will study Werner's theory. Okay, it's a very simple theory. Maybe after this we'll be able to wind up. Okay, so Werner, who is actually called as father of coordination compounds, right? Because he was one of the very few scientists who started to study about this coordination compounds, because nobody had any idea. Everybody thought that our coordination compounds are very similar to your double salts, like say Epsom salt, Mohr salt, like that. They thought, okay, they are also going to be similar to your double salts. Okay, Werner was the first scientist to speak about these coordination compounds, right? And for this, he won the Nobel Prize also. I think, I don't know the exact year, I think it was in some 1800s. Okay, he won the Nobel Prize for chemistry for his work on coordination compounds. Okay, so that's why he is called as father of coordination compounds or father of coordination chemistry. Okay, right. So even though now you will feel that whatever we are going to study is very absurd, right? Now we might not be able to appreciate it because we have so many advanced theories right now, right? But at that moment, at that particular time era, whatever he said, people treated him like a god. Right, because nobody was able to understand anything, but he was the one who tried to understand the things which nobody was able to understand. Okay, right. So what he said is that, obviously we're going to study about coordination compounds only. What he said is that the central metal atom, the metals, I would say in general, the metals, right, are going to have two kinds of valencies. Okay, he said metals are going to have two kinds of valencies. One are what are called as their primary valencies, right? And other thing is what is called as your secondary valencies. Okay, so he said that metals in general can have two types of valencies to be satisfied. Okay, one are what are called as primary valencies, the other one are what are called as secondary valencies. Okay, so he said these primary valencies can be satisfied. It can be satisfied only by anions. Right? He said that these primary valencies are satisfied only by the anions, and these primary valencies are nothing but your oxidation states. Right? These are nothing but your oxidation states of the metal. Right? Obviously, since they are positively charged, they will be able to be satisfied only by negative charge. These are anions. Okay, so indirectly, primary valencies means we're talking about the counter ions. Right, now we can understand. Okay, now we'll be able to understand that the primary valencies are going to be satisfied with the counter ions, which are going to be in the form of anions. Because you will understand that outside the coordination sphere, we always write only negative charges. Right, we always write only the negative charges. Right, so basically primary valencies are nothing but the counter ions. Now, how many number of counter ions we need? That is what is called as primary valence. Okay, right? And yeah, so now when I go for the secondary valence, right? Now secondary valence is satisfied by the ligands. Now these terms were not there initially, ligands and all, but for our understanding, we are seeing what exactly is secondary valence. Okay, these are satisfied by ligands, and obviously we know they can be negative, right? or they can be neutral also. So we have to understand that the secondary valencies can be satisfied by neutral as well as negative species. Those are what are called as ligands. Okay, and these secondary valencies are nothing. They represent. They only represent the coordination number of the metal. Is it not? Obviously, the ligands only specify the coordination number of the metal. Okay, right? And these are nothing but ligands. That's it. These are all the things you need. These are all the things you have to know about your primary valence and your secondary valence. Okay. Now, how did he come to know? Right? How did he come to know that these kind of valencies exist? Right? How did he come to know that okay, there is something called as primary valence, there is something called as secondary valence? How did he come to know come to this conclusion? Is by doing some experiment. Okay, is by doing some experiment. What experiment he did? Let us try to understand. Okay, so he took the experiment of Ni compound, nickel compound, right? Yeah, right. So he took different cobalt, Cl, and ammonia containing compounds. Okay, and he did some experiments. Right now, what he did is, he first took this complex CO, Cl 6 times. How many NH3s? Okay, CO, Cl 3 times. So sorry. Right. The first compound he took was CO, Cl3.6 NH3. Now remember that at that time there was no coordination sphere, there was no bracket, nothing. All they were able to represent the form of a double salt only. This is how he represented. Okay, CO, Cl3.6 NH3. Okay. Now he took this compound and he made this react with excess AgNO3, silver nitrate. Okay, he made it react with excess amount of AgNO3. Okay, now what was formed is he found out that he was forming 3 moles of AgCl. He found that therefore he is forming 3 moles of AgCl. Right, that means all the 3 Cls which are here, right, are coming out as 3 Cl minus ions. Okay, all the 3 he saw was all the 3 chlorine atoms which are there are coming out as 3 Cl minus ions. Right. So obviously, what is understood is that this particular part is able to ionize as Cl minus. That means the other ammonia part is not going to get ionized. That is what he understood. Right. So he was able to write the formula as CO NH3 6 times. Right, that was okay, right? And obviously, this was 3 plus, right? And the other thing are going to be what? Other thing is obviously going to be 3 Cl minus. That is what is understood. Okay. Now we know that whatever is inside the coordination sphere will not be able to dissociate and form ions, right? Whatever is outside the coordination sphere, they will be able to ionize and form ions. Is it not? Right. So he found out that there are 3 moles of AgCl produced, and that is understood that all the 3 Cls are actually going to be counter ions. So in this case, this is your primary valence, right? And your ammonia is actually going to be your secondary valence. Right? Okay. Now, if at all I take another kind of example, right? He took second case, CO, Cl 3.5 NH3. Again, this was another compound, right? Again, he made excess AgNO3. Right? Now, what he found out is he was forming only 2 moles of AgCl. Right? He was forming only 2 moles of AgCl. So, what can we conclude here? Obviously, we are getting only 2 Cl minus ions. Right? Out of the 3, we are getting only 2 Cl minus ions. So obviously the other one is going to be inside the coordination sphere. Right? So the formula he decided was CO, Cl, NH3, 5 times 2 plus. Is it not? Now you understand that anion or a neutral species can be a secondary valence. Right? And this is going to be your primary valence. Right? Say if I give another compound, I think you will be able to do this. If I write CO Cl3.4 NH3, now what happens? We can understand that if I put AgNO3, excess AgNO3, he found out that there is only 1 mole of AgCl he was able to get. Right? He was able to get only 1 mole of AgCl. So we understand that out of the 3 CLs we have, right, only one of them is going to come out as CL minus. So that is going to be the primary valence. The other 2 CLs are going to be inside the coordination sphere. So that is going to act as secondary valence. So we can conclude that only one CL minus ion, and the formula can be decided as COCl2 NH3 4 times. Right, NH3 4 times, and this is going to be plus. Okay, this is going to be plus, right? So we understand that this chlorine and your ammonia are going to act as secondary valencies, right? And then this Cl minus, one Cl minus is going to act as a primary valence, right? That is all he did, right? He was able to say that only the primary valence will come out as the ion. The secondary valences cannot undergo ionization, right? That is all is decided. That is why we say metal is going to have 2 types of valencies. One which cannot ionize, the one which can ionize. Very, very simple, right? So that is all about your Werner's theory, because again, no other information is there. Nothing about the strength of the complex, nothing about the shape, nothing about the geometry, nothing was told. But he was the first one to even attempt that these kind of experiments, and he was able to give an insight. Okay, this kind of different, entirely different chemistry itself exists. Okay, and that is all about your Werner's theory, right? So we completed Werner's theory, we completed your valence bond theory. Okay, only one thing is left, that is a CFT. I think I'll be able to complete this in the next class. Okay, and we'll move on to next chapter. What chapter you want to move on to, people, after completing this? Any suggestion? What?
Chemical kinetics.
Chemical kinetics. Okay, we can go to chemical kinetics. Okay, chemical kinetics is again going to be very small because half the chapter is deleted. I don't think you have Arrhenius equation and stuff. Activation energy, all those things are not there, right? So you'll be able to easily complete in 1 or 2 classes. You'll be able to easily complete your chemical kinetics also. Okay. After that, what is left? After that, I think surface chemistry is left, right? Surface amines is there. Oh God, that's a big chapter, right? Not a big chapter, but again, a lot of things to study. Okay. So surface chemistry is little small. Okay. So we'll finish chemical kinetics, then we'll go to surface chemistry, then we'll go to amines. And as I told you, for D and F log, we can take care. Okay, D and F log, I told you the questions are going to be very less, right? Even if they ask, they'll be asking only from laminar contraction and anti-archival contractions only. Okay, right? Other than that, if you have any doubts, you can always ask me in D and F log levels, right? It is very boring to teach these kind of chapters. Okay, P block, D and F block, and all are very boring to teach, and it is very boring to listen also. That's why I'm not taking. But if at all you want me to teach something, if at all you have any specific doubts, yes, we can see that. Okay, right? So I will talk to Raghav. I think from next your excellence is physics and math is completed, right? Someone told me it is completed. Math and physics in excellence.
No, sir, it's not completed yet.
No, sir, it's not completed.
It's not completed. Okay. So once he completes, maybe then only I can take his classes also. Okay, fine. Let me see what I can do. Right? Or people from I will at least inform this. At least from next, we have class on Saturday, right? So all the Saturday classes, we can have a 2 hours class, right? Right now only I'm telling, and it will be confirmed by your excellences management also. Okay. From next Saturday, right? We will have 2 hours.
Friday, right, sir?
Friday.
Friday. Yeah, Saturday is for 11th. Yeah, correct. Friday, right? So that Friday, every Friday we'll have 2 hours of class, right? 1 hour we'll teach. We'll have a 10 minutes break. Again, we'll have 1 hour. Okay. Right, that we'll do, so that we'll be at least have half an hour extra, so that we'll be able to complete the syllabus. Any idea, people, when the board exam is going to happen? Any news came? Anything?
Yes, sir. It starts from April 26th. Got the circular.
Okay, got the circular.
Yes, sir.
Okay, April 26th. That means we have time. Okay. Fine, we'll see. It is better to complete soon and go for more and more number of revisions. That will be better. Okay, we'll see what we can do. Okay, any questions, people, from this coordination compounds, whatever we saw today? Any questions anybody wants to ask?
Sir, no doubt, sir.
No, sir.
Okay, people. Thank you so much. We'll meet again next week.
Thank you, sir.
Thank you.